Today is the ninth day of myself doing and explaining you all the chapter Organic Chemistry, some basic principles and techniques. Okay, the first period. Now, in the previous class, I had explained you about resonance. Today, I'll be trying to explain you about the effect, resonance effect. And this resonance effect, it is called Mesomeric effect. It is called Mesomeric effect. Now, to understand Mesomeric effect, have a look very carefully. The mesomeric effect is the permanent effect involving the transfer of electrons relate through a pi electrons of multiple bonds. When I say pi is this one. Pi electrons of multiple bonds in a chain of carbon atoms in a molecule, and this is called mesomeric effect. It is a permanent effect, remember that. Involving what? The transfer of electrons. Involving the transfer of electrons relate through pi electrons of multiple bonds in a chain of carbon atoms. I would like to show you one example over here. For example, if I draw a structural formula of an organic compound CH2 double bond CH2, I am trying to explain you mesomeric effect. Okay, so please watch very carefully. CH double bond CH, then single bond aldehyde group CHO, this way CHO. Okay, CHO. Okay, now have a look at this very carefully. Okay, now as you can see on your screen, there's an organic compound CH2 CH CH double bond CH CHO. This is an aldehyde group over here. Now on the aldehyde group you can see there is an oxygen electronegative. So what it will happen is it will pull the pi electrons on itself like this. If this happens, then the alternate multiple bonds are also pulled this way. It gets pulled this way, and this way. So this movement, it is called mesomeric effect, and it is a permanent effect. It is a permanent effect. It will result in the formation of a species which looks like this. H2C. This carbon will carry a positive charge. There is a single bond. CH. There is a double bond over here. Then there is CH, single bond, CH, okay, double bond CH, and then over here O minus, because this has fallen over. The pi electrons have fallen on the oxygen atom, giving it a negative charge. So it is a permanent effect which is being relayed. Transfer of electrons relayed through the pi electrons of multiple bonds in a chain of carbon atoms in a molecule, and which is called mesomeric effect. So this was one example to explain you mesomeric effect. Resonance is already clear to you. Okay, this is also delocalization of electrons permanently, and the effect is called mesomeric effect. You should remember that this mesomeric effect, it is a permanent effect and comes into existence in the following two cases. When an electron withdrawing or electron, this is an electron withdrawing group. When an electron withdrawing or electron pumping group is in conjugation over here. Double bond, single bond, double bond, single bond, double bond. This is called conjugation, the pi bond. Then, when an atom or group having at least one lone pair of electrons, an atom or a group having at least one lone pair of electrons is in conjugation with a pi bond. That time also this is possible. I want to explain this with the help of another example. Let me put another slide over there to explain you the next example. For example, if you have a look very carefully, the next example for mesomeric effect, I will take this example CH2 double bond CH single bond, and let me put let's put Br, bromine. So this bromine, we know it has lone pair of electrons in its valence shell, 1 2 3 4 5 6. One is used over here. Now this lone pair of electrons, it is in conjugation with this pi electron system over here. So what will happen? This lone pair, if it falls over here on this single bond, this pi electron is disturbed, so it is thrown on the vertical adjacent carbon atom, giving a structure which looks like this: CH2 dot dot dash single bond, CH, double bond, and then this Br will have two lone pairs and it will carry a positive charge. So this is an example of mesomeric effect, which is a permanent effect. Now moving further to different types of mesomeric effect, there are basically two types. One is positive M effect, and the other one is negative M effect. Negative M effect. There are two types of effect. One is plus M effect, the other one is minus M effect. This I'll explain you from the other slide. Let's have a look on the other slide. There is resonance, and I'll come back to this resonance after some time. Now, let's quickly finish off this mesomeric effect, which is called M effect also. Now, this refers to the polarity produced in a molecule as a result of interaction between two pi bonds or a pi bond and a lone pair of electrons. So, if there is a interaction between a pi bond and a pi bond or a lone pair of electrons, then the effect becomes mesomeric effect. Now here, the electron withdrawing or releasing effect attributed to a substituent through delocalization of pi electrons, which can be visualized by drawing various canonical forms, is known as mesomeric effect or resonance effect. It is symbolized by either capital M or capital R. So you have seen over here, canonical form is here. There is a canonical form. Okay, now that is a canonical form. Going further to different types, as I was talking about some time ago, the mesomeric effect is negative when the substituent is an electron withdrawing or pulling group. If it pulls electrons, that time it becomes negative. The pulling group, some example of group which pull electrons, it can be, examples here only. O minus, NH2, NH, this one minus M is NO2, CN, S, OH, CHO, CO, all these are electron pulling, electron withdrawing groups. So they will show minus N effect. Okay. Whereas the groups and the effect that is positive when the substance is an electron releasing group, electron pumping group, electron giving releasing groups. Examples are here. You can see. All these are examples of groups which which provide electrons along the chain. They will pull electrons away from the carbon chain. So these are the two types of effects under mesomeric effect. Okay. Now let me give examples specifically in the next slide. Have a look very carefully. Positive mesomeric effect, plus M or plus R. Now have a look. In phenol, the OH group shown plus M effect. It shows plus M effect. You can see it has two lone pair of electrons. It is pushing electrons in the ring. Okay, so what is happening after that? Resonance is happening. Okay, so due to delocalization of lone pair on oxygen atom towards the ring, thus the electron density on benzene ring is increased, particularly on ortho and para position. So if there is a ring like this, okay, ortho, meta, para. So ortho, meta and para position. So ortho and para position particularly. So the electron density on the benzene ring is increased where? On the ortho position and the para position, because of this positive M effect. Because there is a group phenol, in phenol there is an OH group on one of the carbon atoms. So this lone pair of electrons is being pushed towards the benzene ring, and it is causing positive mesomeric effect. Now, moving further to the next effect, next type of mesomeric effect, which is called negative mesomeric effect, minus M or minus R. The negative mesomeric effect, minus R or minus M, shown by a cyanide group below. It is called acrylonitrile. Acrylonitrile, it is a compound which is used in adhesive bonding, bonding tiles or bonding, bonding like plastics and all. This compound acrylonitrile is used. Okay, now that is coming under industrial chemistry, but here this group, a cyanide group present in this compound acrylonitrile, it shows a negative mesomeric effect due to the presence of the cyanide group. The electron density on third carbon decreases due to delocalization of the pi electrons towards the cyanide group. Okay, now look at it very very carefully. This nitrogen, it is pulling electrons. It is pulling the pi electrons on itself. Okay, like this. And because of this pulling, these pi electrons are getting pulled on this single bond. So there is a charged species being formed. Okay, like this. This carbon will carry a positive charge, no charge. This nitrogen will carry a negative charge after that. So that is an example of mesomeric effect. Okay, remember mesomeric effect. It is a permanent effect involving the transfer of electrons which are being relayed through pi electrons or multiple bond in a chain of carbon atoms, conjugation in a molecule, and that is called mesomeric effect. Okay, now, now let me come back to resonance energy before going further. Now see, in the case of resonance energy, the greater the predicted stability of a resonance contributor, the more it contributes to the resonance hybrid. Like resonance hybrid is shown normally like this, resonance hybrid of benzene. Okay, the greater the number of relatively stable resonance contributors, the greater the resonance energy. Okay, relatively stable resonance, that means more the number of structures, canonical structures, the better it is. That will add up to the resonance energy. The more nearly equivalent the resonance contributors, the greater the resonance energy. That means the number of resonance contributors, if it is more, the resonance energy will also be quite markable. Okay, remarkable. Now, come down to hyperconjugation, which is called no bond resonance in this organic chemistry chapter. Resonance because of no bond. Hyperconjugative effect because of no bond. Okay, now we have studied already, understood already inverting effect in the alkyl groups. Okay, on a saturated carbon chain, as is given in the previous classes. I have explained you. Okay, inverting effect. Okay, now in this class, today's class, this hyperconjugation I'll explain you. Now this hyperconjugation over here, the displacement of electrons, it takes place through a different mechanism. It takes place through a different mechanism. Okay, and this different mechanism is known as hyperconjugation. Okay, and this hyperconjugation, as I've already told you, it is called, it is no bond resonance. No bond exists between the carbon or the hydrogen, but those two atoms are very closely, they are not far away from each other. Now here, point wise, the electrons of the sigma bond between carbon and hydrogen are involved in delocalization. In structure to the right, if you see over here, no bond between carbon and hydrogen due to migration of the sigma bond is seen. See, there is no bond over here. Okay, both these electrons are broken. Both these electrons are broken, and a multiple bonds form over here, but this separates and becomes a hydrogen ion over here. So, but they are close to each other. So this is also one type of resonance happening over here because of no bond between this carbon and this hydrogen, and that is called hyperconjugation. Hence we call hyperconjugation also as no bond resonance. Now this hyperconjugation, if you see, this does not indicate that hydrogen is completely detached from the structure, but some degree of ionic character in the carbon hydrogen bond and some single bond character between carbon carbon double bond is seen. Okay, so one very good example is shown in the diagram illustrated below. Okay, I can show you one example for hyperconjugation by an example myself. Let me introduce a new slide over here to explain that hyperconjugation effect. Hyperconjugation effect or hyperconjugation. So have a look very very carefully. It is a very nice and interesting topic under this part of the chapter. CH3, then CH double bond, CH2. Okay, now this is the structure. It is an alkene. So you can see there is a double bond, there is a single bond, conjugation. Okay, now this pi electrons, here in this case, it is moving to this carbon. It is moving to this carbon containing more hydrogen atoms. containing more hydrogen atoms. So if this happens, then any one of these three hydrogens can be detached. Okay, so if let's take, if this two electrons fall over here and this hydrogen is detached, so we get another structure. We get another structure like this. Hydrogen is there, carbon is there, hydrogen is there. This hydrogen has left in the form of hydrogen ion, but it is not gone far away, it remains there only. And then this carbon and the other carbon, there will be a double bond, CH, and then here single bond, CH2, and this pi bond has fallen over here, so there will be a two electrons and a negative charge. So this is the first structure. Further, again, you can have another structure for hyperconjugation when this hydrogen is detached. So I can have H plus C, here also H, here also H, okay, double bond, CH, single bond, and then CH2, two electrons and a negative charge. Okay. Again, I can have one more structure by detaching this hydrogen, so I can have H, C, H over here, H plus double bond, CH, single bond, CH, 2 and double two electrons and a negative charge. So these are the structures. These are the structures which from which we can understand hyperconjugation effect. Okay. Now this hyperconjugation effect, it is an extension. Remember this also. Hyperconjugation effect is an extension. It is an extension of resonance. It is an extension of resonance also. We can call it extension of resonance also. But resonance and hyperconjugation are different. Resonance involves conjugation of lone pair of electrons or pi electrons, whereas this hyperconjugation involves conjugation of sigma electrons. Here there is conjugation of what? Sigma electrons of carbon hydrogen bond with pi electrons of the double bond. So that was all about hyperconjugation. Example. Now, on this basis of hyperconjugation, let us understand the order of stability of a carbocation. Now, what is a carbocation? Carbocation, an organic compound, a hydrocarbon which has a central carbon atom carrying a positive charge, becomes a carbocation. So, I have explained you in the previous classes the degree of the carbon atoms, central carbon atoms. Like this one, if you see CH3, methyl group, a methyl carbocation. This is a methyl carbocation, carbon carrying a positive charge. You can say it is 1 degree. Okay, it is 1 degree. This carbon also is 1 degree, attached to at least one carbon atom. This carbon is 2 degree. This carbon is 3 degree. Okay. Now, if you look at the relative stability over here, the order of stability of carbocations is given over here. If you look at the first one over here, this has 9 hyperconjugable hydrogen atoms. That means 3 here, 3 here, 3 here. No bond resonance. Okay. So that adds to its stability. This is more stable. This becomes more stable. This has 3 plus 3, 6. 6 hyperconjugable hydrogen atoms. So slightly lesser stable. This has 3 hyperconjugable hydrogen atoms, so it is lesser stable. But this has no hyperconjugable hydrogen atoms, so this is the least stable. That means this becomes the most reactive. This becomes the most reactive. This becomes the least reactive. So we can ask two questions from your concept based. I can give you a 3 degree carbocation, a 2 degree, and two 1 degree carbocation, and ask you among these arrange them in the order of increasing order of reactivity or decreasing order of reactivity. Two questions already, and I can ask you also arrange them in the decreasing order of stability also or increasing order of stability. So you must use your concept over here of this understanding on the basis of hyperconjugation and answer the question. Okay, so that was all about hyperconjugation. Now moving to further to my next slide over here for a few examples. Hyperconjugation, I have given some examples over here. Okay, this is a carbocation. it has total number of structures, four structures. This is one structure, and three from one, two, three. It becomes four structures. This is one structure. It can have one, two, three, six, seven, seven structures. Okay. This has three plus three, four, five, six. Okay, and one 10 structures total. So the more the number of structures having possessing no bond resonance between the carbon and hydrogen, it helps in the stability, increasing the stability of that organic compound. Now, this uh, this what we call hyperconjugation, as I've told you already, it is also known as sigma bond resonance. It is known as sigma bond resonance. Now, this hyperconjugation it depends on the number of alpha hydrogen present in the compound. What are the alpha? The hydrogen atoms link to the alpha carbon after the carbocation center. For example, if I draw the structure like this, CH, CS3 like this, and there is a carbocation over here having two hydrogen like this. Okay, this is the main carbon one. So this adjacent to this carbon one, this is alpha carbon, and these are the alpha hydrogens. These are the alpha hydrogen atoms. So here you must remember this hyperconjugation depends on the number of alpha hydrogens present in the compound. More the alpha hydrogens, more number of ways in which a structure can be represented. Hence, more will be the stability. In the given above picture, the last structure is more stable due to more number of alpha hydrogen atoms. This can be explained by inductive effect, but hyperconjugation is given preference over here. So please remember, these can be explained by using plus I effect, because methyl groups they exert or they exhibit plus I effect. Okay, so here, because of this plus I effect of the methyl group, which is inductive effect, the better stability is provided by hyperconjugation. That's why hyperconjugation takes a dominance over the inductive effect. Okay. Now, moving further to my next slide. Now, quickly, I revise everything whatever I have taught you till now. Here, the fundamental things in organic reaction mechanism. A covalent bond can undergo breaking in two ways. One is homolytic fission or homolysis. Another one is heterolytic fission or heterolysis. In detail over here. Homolytic fission, in this process, each of the atoms acquire one of the bonding electrons. So that means they are separating equally two similar types of species. The products A dot and B dot are called free radicals. They are electrically neutral and have unpaired electron associated with them. Homolytic fission is the most common mode of fission in vapor phase. Alkyl radicals are classified as primary, secondary, or tertiary. Alkyl radical stability increases as we proceed from primary to tertiary. That means, so you have to remember over here. As we proceed from primary to tertiary, because of plus I effect and hyperconjugative effect, the stability also increases. That means this is most reactive and the reactivity decreases because of more stability on this side. Now, this was regarding homolytic fission or heterolysis. Coming to the next slide, for heterolytic fission. In this process, one of the atoms acquires both of the bonding electrons when the bond is broken. So, one of the groups which is more electronegative, for example, in the given example below, B is more electronegative. So, if B is more electronegative than A, which thereby acquires both the bonding electrons and becomes negatively charged. So, here what happens? It pulls both the electrons which are shared between A and B, and it acquires a negative charge. So, this is an example of heterolytic fission. So, the presence of an electronegative element plays a remarkable role in understanding what type of fission generally takes place. Further, in organic chemistry, there are reaction intermediates also. When a reaction is happening between the two reactants, before the products, there is something called reaction intermediates also forming. Now, heterolytic and homolytic bond fission results in the formation of very short-lived species or fragments called reaction intermediates. Among the most important reaction intermediates are carbonium ions, carb anions, carbon free radicals and carbines. Okay, carbines are like this, CH2 double bond like this, two electrons. This is carbene. Okay, methyl free radical we can say CH3, one electron on the central carbon atom. Carbocation means C plus H3. Carbanion means CH. You can have three over here, two electrons like this, carbanion. So these are examples of free radicals. Now, carbocations, organic ions which contain a positively charged carbon atom, are called carbonium ions or carbocations. They are formed by heterolytic fission. So example is given over here. If there is a more electronegative element over here, okay, that will take both the electrons on it. So whatever is formed as a result of this fission, it is called a carbonium ion or carbocation. But here for the formation of carbocation, generally the atom which is leaving, it should be a more electronegative atom. Okay. Now moving further in this chapter, tertiary carbonium ions is more stable than secondary, which in turn is more stable than a primary because of plus I effect associated with the alkyl group. Along with plus I effect, we can talk about hyperconjugation effect also. So please learn this order. Please learn this order. The stability of this is highest because it has three plus I effect from three methyl alkyl groups. Okay. This has two plus I effect. This has one plus I effect. Okay, because there is only one alkyl group. Okay. Now, moving further, carbanion, organic ion which contains a negatively charged carbon atom is called carbanions. They are also formed by heterolytic fission. Whenever fission takes place unequally, heterolytic fission, okay, that time we get a carbanion as well. Over here, this Z, the leaving group, it is less electronegative. That's why both the electrons which are shared, they have fall on the carbon atom. That's how we're getting carbon ion. Okay. Now, where Z is less electronegative species than carbon, a primary carbanion is more stable than secondary. So primary is more stable. This is reverse order than the carbocation. Okay, which in turn is more stable than a tertiary because of plus I effect associated with the alkyl group. So remember this order also, which is important. I will ask questions from here also. Then moving to the next type of intervertical reactive intervertical, this reactive species, which attacking species or attacking agents. The first type is called electrophile, electron loving. It is positively charged or neutral species which is electron deficient. Example is He, helium, H2O plus, CS3, all carrying positive, NH4 plus, AlCl3, SO3, okay, CHCl2, CCl3. All are acting as electrophiles. They are themselves carrying positive charges. Okay. Now, nucleophiles, it is negatively charged or neutral species with lone pair of electrons, HO minus, hydroxyl, cyanide, water, R3N, R2NH, etc. So these are two types of reacting species or reagents which are attacking reagents, okay, in organic chemistry. So remember, electrophile means electron loving, nucleophile means nucleus loving. So nucleophiles attack what? The positive centers. Electrophiles attack the negative centers. After that, moving to the next slide, we can see electron displacement effect in covalent bonds. This is something which I have explained in the previous classes very nicely, but here I have given some data. Data means some writing things with respect to the electron displacement effect. Bonds. Electronic displacement in covalent bonds occurs due to the presence of an atom or group of different electronegativity or under the influence of some outside attaching group. So this displacement happens of so many things, either due to the presence of an electronegative group or the influence of some outside group which is coming to over there or which is already attached. Because of this displacement, number of effects are observed. One is inductive, I have explained you already. Electromagnetic effect is there, resonance or mesomeric effect is there, and hyperconjugation effect is there, which I've already explained in detail. Okay, this is a summarization of whatever I have taught you till the previous classes. Then, inductive effect I've already explained you. Okay, it involves carbon electrons. The electrons which form a covalent bond are seldom shared equally. between the two atoms. So due to difference electronegativity, electrons are displaced towards the more electronegative atom. This results in the inductive effect. There are two types, plus I and minus I. Okay, so you can read through this carefully on your own. Moving to the next slide. Over here we have groups exhibiting minus I effect. Okay, try to remember some of them. Groups exhibiting plus I effect. Examples are here. Okay, and inductive effect is not confined to the polarization of one bond. Okay, so it is not confined to one bond. It goes further, but it becomes weaker slowly and slowly. Okay, thus the inductive effect of carbon 3 upon carbon 2 is significantly less than the effect of the chlorine atom on carbon. So it becomes weaker and weaker and weaker as it moves further in the chain. Further, resonance structure, I have already explained the resonance of phenol. Okay, a number of organic compounds cannot be accurately represented by one structure. For example, benzene is ordinarily represented as like this, but we can write benzene in this way also. Okay, this is the canonical structure, or I can write benzene in this way also. Okay, this way also it is possible. Okay, all are similar. Okay, now this structure, the above structure has three carbon-carbon bonds and three carbon-carbon double bonds. Okay, this is the double bond. Okay, now the carbon-carbon double bond is it is shorter, 1.34 angstrom. But the carbon-carbon, we can talk about the double bond. Short, single bond is shorter, double bond is, you can see, 1.34 angstrom. So the double bond is shorter than a single bond. Single bond is longer. But it has been determined experimentally that all carbon-carbon bonds in benzene are identical and have same bond length of 1.39 angstrom, somewhat average between a double and a single bond. Okay, so here we have the structures of benzene, which is represented by resonance. Okay, structures 1 and 2. Okay, then another example of resonance is provided by a compound which is called nitromethane CH3NO2, which can be represented by two Lewis structures. CH3NOO. Over here, this oxygen is carrying a negative charge. So the first structure, resonating structure, nitrogen positive charge, and the other one CH3N plus O minus over here, because there has been what, movement of electrons, displacement of electrons because of the more negative atom or group. The actual structure of nitromethane is a resonance hybrid of the two canonical forms 1 and 2, so which can be represented this way: CH3N, okay, bond oxygen, and then we can put dot 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 like this, dot dot like this. Okay, delta negative, and over here we can put delta positive. So this becomes the resonance structure hybrid over here. Okay, that is the method of representing a resonance hybrid for a compound which is called nitromethane. Okay, now the difference in the energy between the most stable contributing structure for a compound and its resonance hybrid is called as resonance energy or resonance stabilization energy. So you learn this definition from here for resonance energy or resonance stabilization energy. Okay. Then moving to resonance effect or mesomeric effect, which I've already explained you. This will give you a very good what we call idea from here regarding resonance effect or amp effect. So we can read through all this. There are two types of resonance structures, plus M, minus M. Okay. Groups exhibiting plus M effect as examples are here. Okay. Negative M effect groups examples are here. One example for aniline I have given over here. Okay. For plus R effect, okay, minus R effect by taking nitrobenzene, plus R effect of aniline. Okay. Then electromagnetic effect. Okay, that is also called E effect. Okay. So here the electromeric effect refers to the polarity produced in a multiple bond compound when it is attacked by a reagent, when a double or a triple bond is exposed to an attack by an electrophile, that is E. Okay, so this has been explained. If there is an electrophile which is coming in the presence of a reagent, so there is displacement of electrons, pi electrons, which is being displaced on one of the atoms. So this causes a production of species which is polar in nature. Okay, so I will, it's already time up, so I'll just stop over here. I'll explain again in the next class from this electromagnetic effect in detail and try to complete the chapter in my next class. Please hang on over there so that I will take the attendance before you all leave the class and join the next class. Okay, just hang on over there. Okay, I have downloaded the attendance list. Now you may leave the class. Have a nice day.